and some properties of the dot product. Come up here. We have one that is really nice, and you'd hope this was true. It's not going to be true for the next product that we talk about, but u dot v equals v dot u. So this is a way of looking at it here. So I've got this diagram. Okay. Here's u, here's v. If we're going to look at u dot v, so the left side of this formula, u dot v equals the magnitude of u times the magnitude of v times cos theta. If I just put the magnitude of v times cos theta in brackets, we know that that's the scalar projection of v onto u. So scalar projection of v onto u, so perpendicular line here, there's magnitude of v cos theta, times magnitude of u, so there's u dot v. Okay. On the other side, v dot u, well, v dot u is magnitude of v times magnitude of u cos theta. Put brackets around this part. This part here is the scalar projection of u onto v. Multiply that by the magnitude of v, and you got v dot u. Okay, so that's this one here. Magnitude of u cos theta down here times the magnitude of v. That gives us v dot u. So left side, u dot v equals magnitude of u times magnitude of v cos theta. These are all scalars, so you can rearrange them whatever order you want. So I'm switching the v and the u. Now we have the formula for v dot u, and you can write it that way. So it equals the right side. So that's that property. Okay. So here's some other interesting facts here. So when theta equals 0 degrees, okay, cos theta equals 1. You know that cos of 0 is 1. If that's true, then u dot v must equal magnitude of u times magnitude of v. And this is the scenario, this is what it would look like. U and v are heading in the same direction if theta equals 0. And the shadow of u onto v is just u. It's the same thing. So you're just multiplying their magnitudes. Okay. Also, because cos 0 equals 1, the cos theta part here just gets replaced with a 1. When the angle is between 0 and 90 degrees, well, we've got a different situation. Okay. If theta is between 0 and 90, then we know that cos theta is between 0 and 1. Okay, so we said that when theta is between 0 and 90, cos is positive. The greatest that cos can be is 1. So we have this situation. And if that's true, then u dot v is never going to equal the magnitude of u times the magnitude of v, because cos theta is less than 1. So when you multiply magnitude of u times magnitude of v times cos theta is less than 1, this is the max it can be. So this is going to be positive. Whenever the angle is between 0 and 90, u dot v is going to be positive. Okay? And this is what the vectors would look like. What about when theta equals 90? So this is an important one. When theta equals 90, cos 90 is 0. The projection of u onto v is 0. So when you multiply that, the projection of u, scalar projection of u onto v, times the magnitude of v, it's just going to be 0 times the magnitude of v. So u dot v is 0 whenever the vectors are perpendicular. When the angle between them is greater than 90 but less than 180, then cos theta is between -1 and 0. Okay, so between 90 and 180, so between 90 and 180 here, cos theta is between 0 and -1 here. But we start with a smaller one, so -1 to 0. Okay? And if that's true, then you're multiplying the magnitudes by a negative number. So u dot v is going to be between negative magnitude of u and magnitude of v and 0. So u dot v is going to be a negative value. And the vectors will look like this. Okay? So when you're dot producting these two vectors, you're taking a negative projection here times a positive number, you're going to get a negative number. And the last case, when theta equals 180 degrees. Theta equals 180 degrees, cos 180 equals negative 1. Okay? So u dot v is magnitude of u times magnitude of v times cos theta, but cos theta is negative 1. You're going to get the negative here. Okay? This is what they'd look like. You're going to get a negative number times a positive number. Doesn't change the size of the vectors when the angle is 180. So they're in the same on the same line. So you get this as the dot product. And another property here. So if you've got a vector dot product with itself, well, the angle between a vector and itself is 0 degrees. Cos of 0 is 1. So we get this nice little formula. So magnitude of u times magnitude of u, which is the magnitude of u squared. So a vector dot itself is just the magnitude of that vector squared. Okay. Another name for the dot product is called the scalar product, because in all these, when you dot the two vectors, you always get just a real number. Okay? So we're reducing it to one dimension and multiplying the real numbers, so we're getting a scalar. What about this one? So some scalar times a vector, dot with another vector. Well, that's what it would equal here. So ku times v cos theta, the magnitudes. Okay? You can pull that k out. It's not going to change it. Okay, they're all just scalars now. And if you've got this, well, the k outside, magnitude of u times magnitude of v times cos theta is just k times the dot product. So there's one property. And if we keep going and redistributing the k in to the other vector, we also get this one. So we've got this equals this equals this. Okay. And then we have the distributive property. This one is a little longer to prove, so I'm going to direct you to page 373 in the textbook to look at the proof. I'm not going to walk through it here, but we have the distributive property for the dot product of vectors. So u dot v plus w equals u dot v plus u dot w. Okay, so that's nice to have. As a result, we have some of these here that I can show you. So I dot I, a vector dot itself, is just its magnitude squared. Remember, I is the unit vector in the direction of the x-axis. Okay, so I dot I is 1, which also means that j dot j is 1 and k dot k is 1. Okay, I dot j equals magnitude of I times the magnitude of j times cos of 90. We know cos 90 is 0. So when you dot product these two, you get 0, which makes sense because they are perpendicular vectors. Okay, so I, j are perpendicular. When you dot product them, the projection of I onto j is 0 times the magnitude of j, which is 1. Okay, so that's true then for I dot k equals 0 and j dot k equals 0. Okay, what about something like these? So 2I dot 3j equal to 0. Okay. Why is that 0? Because I and j are perpendicular. 2I and 3j, they just change the lengths. They're still perpendicular like this. So their dot product is 0. What about 2I dot 4i? Well, they're in the same direction. So you're really just multiplying 2 times 4. Okay, and you get 8. And then you could do something like this. You can use the distributive law, so 2i dot 4j minus I. Well, you distribute the 2i and 2i dot 4j and 2i dot negative I. Okay. These are perpendicular, gives you 0. These are in the same direction, I and I, but that's a negative. So 2 times negative 1, negative 2, and we get that nice number. And that's it for part 1 of projections and dot product.